50 million years is a span of time that practically defies human imagination. To understand the scale, the entire journey of humanity as a biological species, from crude stone tools to interplanetary ships, makes up less than 1/10 of 1% of this period. The trees standing today in the rainforests of Queensland belong to lineages that originated back on the supercontinent of Gondwana, during the times when Australia, Antarctica, and South America formed a single landmass. They witnessed the continent beginning to break apart. They withstood the meteor strike that wiped out 3/4 of all living species on the planet. They survived several ice ages and just as many warming periods. And then, in just 200 years of European colonization, less than 1% of these forests survived. Fire and the axe almost completely eradicated what had been growing here even before the appearance of the first flowering plants on Earth. It would seem that almost nothing is left. But right now, when the loss seems final, scientists have found a way to bring this forest back to life. This forest is not found everywhere heat and humidity reign. It has survived only in a narrow coastal strip of eastern Australia, stretching from southern Queensland to northern New South Wales, where mountain ranges and the proximity of the ocean have formed an unusually stable microclimate. Moist air masses from the Pacific Ocean rise along the mountain slopes and bring abundant rainfall with them. Deep gorges hold in the cool and damp, maintaining conditions that have long since disappeared on the rest of the continent. These exact territories were included in the UNESCO World Heritage List under the name Gondwana Rainforests of Australia. This is not a single continuous forest, but a scattering of individual forest fragments separated by lands developed by humans, yet united by a common history and the origin of their ancient flora. Some trees living here belong to evolutionary branches so old that the very word ancient loses its metaphorical meaning. Their lineage takes root in eras when the face of the Earth was completely different, and the current continents had not yet taken their shapes. Araucarias, cowries, and southern beeches are commonly called living fossils. Their ancestors inhabited the planet back in the Mesozoic era, at a time when dinosaurs roamed the land. These evolutionary branches have survived for hundreds of millions of years, outlasting global climate changes and the death of entire ecosystems. However, this definitely does not mean we are looking at the exact same trees that live next to Tyrannosaurus rexes. Over millions of years, they changed and adapted to new conditions. What is truly amazing is something else entirely. Their key shapes and characteristic features still recognizably echo the look of their distant ancestors to this day. Southern beeches, or Nothofagus, grew on Gondwana even before it broke apart. When the continents drifted in different directions, their populations were separated by vast oceans. But on different continents of the southern hemisphere, these trees have retained a noticeable resemblance to each other. That is exactly why the Gondwana rainforests are not just a picturesque corner of the wild. They preserve the living branches of ancient evolutionary lineages and give us a chance to see plants whose ancestors appeared long before the continents took on their current shapes. But how did this living archive manage to survive to the present day? The answer lies in the topography of the eastern coast of Australia. While the interior of the continent was steadily drying up, the rainforest retreated into narrow, wet gorges and onto mountain slopes, where the necessary conditions for life still existed. These places became refugia, natural sanctuaries where ancient flora weathered periods of drought and climate shocks. Rainfall here stayed at a relatively stable level, even when most of the continent was getting increasingly dry and unfit for rainforests to survive. During the ice ages, the climate grew colder and drier, but high humidity and the protection of the mountainous terrain allowed the plants to hold on. The forest shrank down to small pockets of suitable habitat, preserving ancient lineages from generation to generation. The forest did not just passively survive. It moved along with the climate and took root wherever conditions still allowed the plants to exist. For tens of millions of years, this strategy helped the ancient flora overcome the gradual changes in the surrounding world. But this strategy only worked because the changes happened slowly. The forest had time to retreat, recover, and adapt. The threat that came later acted completely differently, and against it, neither the mountainous terrain nor the high humidity could offer protection anymore. The threat arrived along with axes, saws, and the economic development of the land. Colonial settlers looked at the ancient forests primarily as a source of valuable timber, and the wet valleys and dense woodlands were gradually turned into farmland. One of the first casualties was the red cedar, a tree with wood that was soft, lightweight, and resistant to rot. The colonists called it red gold, and this valuable material was exactly what drew the first loggers into the forests of eastern Australia. The red cedar vanished at an alarming rate. It took centuries for the tree to reach maturity, yet it was chopped down in a matter of minutes. By the middle of the 19th century, the easily accessible supplies of red cedar in the coastal valleys were almost completely wiped out. Once the red cedar became a rarity, the logging industry turned its attention to other tree species. Farmers followed right behind the loggers, burning away the leftover vegetation and turning the wooded hillsides into pastures and farmland, further destroying the once continuous forest canopy. That was the ultimate paradox. The forests of eastern Australia had survived the splitting of continents, mass extinctions, ice ages, and climate cycles lasting millions of years. However, they proved completely defenseless against a few generations of people who simply wanted timber and land. The damp ravines, which had served as a safe haven for tens of millions of years, became convenient pathways for exploiting the forest. The very same terrain features that helped the ancient plant life survive climate shifts also made the remaining timber stands much easier to access for logging and commercial development. The toll of several generations of logging is measurable. Only a tiny fraction of the subtropical and temperate rainforests of eastern Australia remains. In certain bioregions, only about 1% of the original forest cover has survived. But the surviving forest is not a single, unbroken expanse. It is broken apart into scattered fragments, many of which cover just a few hundred hectares. Fields, roads, and development stretch between them, tearing apart what was once a continuous, living system. Fragmentation is more dangerous than a simple reduction in size. Isolated populations are cut off from genetic exchange, have a harder time bouncing back from fires and droughts, and cannot migrate to keep up with climate change. Each individual patch becomes increasingly vulnerable over time. A solid block of 75,000 hectares and a scattering of small reserves are not the same thing. Even if their total acreage looks comparable, the disconnected patches no longer function as a single forest and cannot maintain their former connections. But there is another level of loss that is impossible to spot on maps. When a forest breaks apart into isolated islands, each one gradually finds itself in genetic isolation. And over time, this process can alter the fate of entire populations. Trees cannot move around on their own. Pollen and seeds only scatter over limited distances. So a few miles of fields, roads, or developed areas can almost completely cut off the exchange of genetic material between neighboring forest patches. In an isolated population, genetic diversity gradually shrinks. Inbreeding becomes much more likely, and the offspring might have a harder time dealing with diseases, droughts, and other environmental changes. The longer the isolation lasts, the harder it is for the population to adapt to new threats. At the same time, over decades and centuries of isolation, each patch can hold on to its own specific genetic traits. Trees from one canyon carry gene variants that are completely gone from the neighboring gorge and cannot be found in a single nursery. Because of this, losing even a small fragment of forest is not just the loss of a few acres. Along with it, unique genetic combinations that took thousands of years to form and are not preserved in any other population on Earth could disappear forever. This is exactly why just giving these areas protected status is not enough. We need to not only save the trees right where they are, but also collect, study, and carefully store their genetic diversity while these isolated populations are still around. Sometimes history unfolds completely differently. Instead of a gradual fade into obscurity, an unexpected discovery happens when a species thought to be long lost is suddenly found alive. Exactly this kind of event took place in one of the remote canyons of New South Wales. In 1994, a group of researchers hiked down into a remote canyon and stumbled upon trees that, according to the scientific understanding of that time, simply could not exist. This was the Wollemi pine, known previously only from ancient fossil records. Prior to this discovery, the Wollemi pine was considered completely extinct. Not rare and not endangered, but known only from geological deposits. Nobody was looking for living trees because the very idea of their existence seemed completely unbelievable to scientists. The canyon turned out to be so inaccessible that for millions of years, neither humans, nor devastating fires, nor many competing species had penetrated it. A small group of trees kept right on growing, while the rest of the world had long considered this lineage dead and gone. The discovery of the Wollemi pine exposed a fascinating contradiction. A species thought to be lost forever turned out to be alive. Yet its very discovery immediately made it more vulnerable. Now saving these ancient trees meant protecting them from the threats that came along with fame. The location of the canyon was classified to protect the trees from collectors and the accidental introduction of dangerous pathogens. The species had returned from oblivion, but now its continued existence depended entirely on constant human protection. Today, the Wollemi pine is grown in nurseries, and its seedlings are shipped to botanical gardens in various countries. The wild population remains extremely small and exists in only one place on the planet, surviving under continuous surveillance. A tree that survived for millions of years in complete isolation is now unable to make it without human help. This paradox changes the very concept of species conservation, as sometimes it is not enough to just protect the remaining trees. You have to create a backup of life outside of their single refuge. While the Wollemi pine remained hidden in a classified canyon, the rainforests of eastern Australia were generally considered safely protected by nature itself. High humidity, a dense canopy, and water stored in the soil made them practically fireproof. The fire season of 2019 and 2020 shattered this belief. The fire swept through areas that were previously considered practically unburnable, including sections of the Gondwana rainforests. Things that seemed impossible to burn were going up in flames. Rainforests never developed a defense against fire because, for millions of years, they simply did not need one. The native trees do not have thick, fire-resistant bark, and their seeds and young shoots die even in relatively mild fires. Eucalyptus forests evolved in constant contact with fire and know how to bounce back after burning. The rainforest formed under completely different conditions, and so fire remains a devastating force for it, one against which many species never had the time to develop any protective mechanisms. Small populations living in just one canyon or mountain range turned out to be especially vulnerable. If a fire wipes out the only habitat for a species like that, making up for the loss is impossible, since other populations might simply not exist. This was not about the complete wipeout of all rainforests. However, the scale of the damage across World Heritage sites turned out to be way more severe than anyone previously thought. The forest lost its natural defense, something that had been considered practically foolproof for thousands of years. The fires reached places they had not touched for thousands of years. This presented scientists with a new question. Why forests that survived tens of millions of years of climate shifts ended up being so vulnerable to a threat that popped up in just a few human generations? For 50 million years, the forest changed along with the climate. Each generation went through natural selection, gradually accumulating traits that were beneficial in the new conditions. The pace of change and the species' ability to adapt remained relatively in sync. Human impact has compressed this timescale down to just a few centuries. Changes that once unfolded over millennia now occur within the lifespan of a single generation of trees. Evolution can't keep up to establish beneficial traits at the same rate. The forest hasn't become weaker. What has changed is the speed at which the world around it is changing. This is the new threat. Living systems are capable of adapting to change, but only on the condition that they have enough time to do so. Climate models indicate that southeastern Australia is becoming hotter and drier. The conditions that led to the catastrophic fires of 2019 and 2020 could occur more frequently and bring even more devastating consequences. We're not talking about isolated climate incidents. Fire seasons are getting longer, droughts are intensifying, and the lulls between extreme events are becoming shorter. These are the very conditions in which the ancient forests of Australia's east coast are now forced to exist. For relict ecosystems, this changes absolutely everything. The fires of 2019 and 2020 might not have been an exception, but a warning of the future, where extreme conditions will hit faster than the forest can recover. Scientists have come to the unsettling conclusion that traditional conservation measures are no longer enough. Banning logging and designating an area as a protected reserve does not guarantee protection from heat, drought, and fire. These new conditions call for a fundamentally different approach. This approach is known as a living seed bank. Instead of storing genetic material in a static form, scientists grow specially selected trees that regularly produce seeds upon reaching maturity to restore damaged forests. A living plantation simultaneously preserves valuable genetic lines and builds a steady supply of planting stock. Unlike cryogenic storage, it does not wait for a future disaster, but actively helps prepare the forests for recovery. A cryobank serves a different purpose. It saves seeds as a backup in case the living collections are lost, while the plantations supply material for actual planting efforts. Together, these systems build multiple layers of protection for genetic diversity. In Australia, several organizations are handling this work. Some collect and store plant seeds from all over the country, while others build living collections of trees. Together, these systems preserve genetic diversity and provide material for future restoration programs. A living plantation is created with a specific goal in mind, as the trees selected today will eventually become the seed source for new plantings. However, before that happens, scientists need to figure out exactly which lineages are better equipped to handle the conditions that are steadily becoming the new climate normal. To solve this problem, researchers survey tens and sometimes hundreds of populations across the entire range of the species. They take seeds and small tissue samples from each tree, record the exact growing location, and then send all the collected material off for genetic analysis. Genetic analysis helps identify lineages associated with resistance to drought and high temperatures. Scientists evaluate not only the outward characteristics of the tree, but also its hereditary traits, which can significantly boost the chances of the plant surviving in a changing climate. Whole genome sequencing makes it possible to study genetic material in much greater detail. It allows researchers to find areas of the genome linked to resilience against harsh environmental conditions, as well as to compare different lineages without relying solely on outward physical traits or the geographic origin of the plants. However, genetic data alone is not enough. Promising trees are planted outdoors, and their development is monitored in a real environment. Only when the results of the genetic analysis match the outcomes of practical trials are the lines included in breeding programs. Field trials are much more than just watching how fast a tree grows. Researchers specifically test the traits that directly determine the survival of the plant in a future climate, such as its ability to withstand heat, drought, disease, and other adverse conditions. For every tree on the plantation, researchers measure the depth of the root system, the thickness of the bark, and how quickly the leaves recover after periods of drought. Resistance to diseases and insect pests is evaluated separately, since these threats become significantly worse as the climate changes. The plantations themselves serve two functions at once, acting as testing grounds and simultaneously providing a source of seeds for the future. The trees grow under conditions of heat and unpredictable rainfall, and researchers continuously monitor their health to identify the most resilient lines. In this way, the exact same plantation accomplishes two goals at once. It helps determine which trees handle the changed conditions best, and after that, it turns the selected plants into seed suppliers for the next generation of restoration plantings. However, these studies revealed another major issue. Trees transplanted into different soil sometimes grew much more poorly than expected. The root cause might not be the genetics of the plant itself, but rather the invisible environment surrounding its root system. Gondwanan trees exist in complex symbiotic relationships with mycorrhizal fungi and soil microorganisms. These bonds developed right alongside the forest over millions of years. A tree can survive without the right organisms, but it has a harder time absorbing nutrients and grows at a slower pace. It turned out that a restoration plan focused exclusively on the trees only addressed one part of the whole ecosystem. The other part lived underground in a complex community of fungi and microorganisms. And without it, fully bringing the forest back to life might be impossible. Researchers at the plantations started looking into ways to restore the native soil microbiomes. A new task was added to the genetic selection and tree resilience testing, which was to preserve or recreate the invisible bonds that had evolved right alongside the forest over millions of years. The scope of the intervention gradually kept expanding. At first, it seemed like just saving the seeds would be enough. Then it became clear that resilient lineages, field trials, and the right soil environment were all absolutely necessary. Every new step revealed just how incredibly complex a real forest actually is. If restoration requires saving not just the trees, but also their invisible connections to the soil, then humans are no longer just growing saplings. They are trying to speed up processes that previously happened through natural selection and the passing of generations. Assisted evolution does not involve creating transgenic organisms or introducing foreign genes. Scientists select and propagate trees that already possess beneficial genetic traits to increase their chances of survival in constantly changing conditions. In nature, beneficial traits spread through survival and reproduction, sometimes over hundreds or thousands of years. But old-growth forests are already suffering from extreme heat, droughts, and fires today, and they no longer have that old luxury of time. Assisted evolution allows us to shorten this journey. Scientists select trees with the necessary genetic traits and use them for breeding, so that new generations can more quickly build resilience to the conditions that are becoming an everyday climate reality. Humans are not creating new traits from scratch, and they are not inserting foreign genes into the trees. They are helping already existing genetic variations spread faster, intervening in a process that used to be driven by natural selection and the passing of generations. This changes the role of humanity. From now on, we influence not only the preservation of the forest, but also the genetic traits of its future generations. Such intervention requires extreme caution, because the consequences of these decisions can last much longer than a single human lifetime. However, assisted evolution only helps species adapt in the areas where they already grow. For some plants, this might not be enough, since climate zones are shifting faster than populations can expand their range naturally. That is when a more radical solution takes center stage: assisted migration. Plants or specific populations are intentionally moved beyond their historical range to places where the climate will better suit their needs in a few decades. This could mean relocating them to higher elevations or further north. The species ends up in a place it would have taken a very long time to reach on its own, but it simply might not have the time left for a gradual range expansion. It is hard to fully wrap your head around the scale of such a decision. We are not talking about a few seedlings in a botanical garden, but about deliberately changing the geographic history of a species that has evolved over millions of years within strictly defined conditions and boundaries. Assisted evolution allows humans to influence which traits will prevail in future generations. Assisted migration goes a step further by involving them in choosing the territories where these generations will be able to exist and continue their development. All of this creates a fundamentally new level of responsibility. Humans are no longer just protecting an existing habitat, they are making decisions about its transformation. The consequences of relocation can last for decades and affect not only the relocated species, but its entire environment as well. However, this is exactly where a difficult question arises. If humans determine where an ancient species is going to live in the future, do they have the right to alter its historical range, even if the chances of this species going extinct become significantly higher without such intervention? This issue has long moved past being a purely philosophical debate. The scientific community has formed various viewpoints on the acceptability of such interventions, and each of them is tied to real risks that must be taken into account before starting major programs. Advocates of a cautious approach focus on the irreversible nature of the consequences. The genetic characteristics of ancient lineages have been taking shape over millions of years, and mistakes made during selection or relocation run the risk of becoming fixed in populations, altering the entire future path of their development. Natural selection works gradually and leaves room for plenty of repeated adjustments. Human decisions are made much faster and can impact a massive number of plants all at once. That is exactly why the fallout from a single mistake can stick around for a really long time. Supporters of intervention push back against this with a different argument. Choosing not to act cannot be seen as a neutral stance, since climate change is already driven by human activity and is unfolding much faster than trees with long lifespans can adapt through natural generational shifts. If humans have destroyed the very conditions that allowed species to adapt on their own, doing nothing could basically mean turning a blind eye to their extinction. Following this logic, being responsible for the damage creates a duty to help fix it. Both sides talk about responsibility, but end up reaching different conclusions. One side warns that people do not fully grasp the consequences of this kind of intervention. The other side argues that this is exactly why we have a duty to step in carefully instead of just walking away from the problem. This debate remains unsettled and keeps evolving right alongside restoration programs. While scientists argue about the limits of intervention, Aboriginal communities in Eastern Australia offer a completely different perspective that does not fully line up with either side. This belief system has been taking shape over thousands of years and exists not in scientific publications or documents from conservation organizations, but in the everyday relationship indigenous communities have with the forest, rooted in a deep connection to specific places and species. For these communities, the forest has never been just a resource to be managed or an ecosystem to be restored. Plants served as a source of food, medicine, and materials for ritual practices, remaining part of a single, living world. The massive logging operations of past centuries severed this connection in more than just a symbolic sense. Communities lost specific plants and places inextricably linked to daily life, knowledge, and cultural practices that had been passed down through the generations over a long period of time. Today, as restoration programs grow in scale, this knowledge is being taken seriously. Indigenous representatives are participating in discussions about which species hold special cultural significance and which plants should be restored first. The difference is not that one approach is right and the other is wrong. The scientific approach asks how to restore the forest. For indigenous communities, the question is framed differently, asking how to renew their relationship with the living environment they were forcibly separated from. While these questions remain unanswered, researchers keep working with seeds, genomes, and soil. However, living plantations cannot be the only line of defense, since they themselves remain vulnerable to wildfires and other disasters. That is exactly why a portion of the collected seeds is sent to cryobanks, where they are kept as a backup fund in case the living collections die off. The living plantation ensures the production of new planting material, while the cryobank protects genetic diversity from completely disappearing. These two approaches tackle different tasks and mutually reinforce each other. If a wildfire or disease destroys a living plantation, the seeds from the vault will allow the entire collection to be restored. If the cryobank turns out to be the only surviving reserve, new plantings will help return the material to the natural environment. A system like this clearly shows that no single conservation method is reliable enough on its own. Using living collections and cryobanks together creates multiple layers of protection, which allows restoration work to continue even after serious losses. Ultimately, living plantations are created for the sake of the seeds, which must return to the damaged forests. But between successfully growing resilient trees and actually restoring vast territories, there is still a difficult gap that has yet to be bridged. Experts estimate that in 5 to 10 years at most, the genetically selected plantations will begin producing abundant seed crops. These quantities could supply major restoration programs, provided the test results hold up outside the experimental plots. This is driven by the biological cycle of the trees planted in nurseries during the early 20s. The first plantings are nearing the age of consistent seed production, a time when material can be harvested regularly and in substantial amounts. Field trials demonstrate that the selected lines handle drought and extreme heat much better than standard planting material. However, strong results at experimental sites do not yet guarantee the same level of effectiveness when restoring vast areas. The high survival rate of the selected lines confirms the promise of this method, but the collected data needs to be verified across different soil and climate conditions. Only then will it become clear whether these successful trials can serve as a foundation for massive forest restoration. Lines that can both tolerate high temperatures better and consume less water are especially valuable. These specific trees are considered the foundation for future living nurseries, which will be capable of supplying material for forest renewal in a changing climate. For the first time, measurable results and clear timelines have emerged. The method has already been backed up by observations of living trees, but its ultimate fate depends on whether the success of these experimental sites can be successfully scaled up to cover much larger areas. While pilot projects remain small in scale, the gap between technical capabilities and actual funding keeps getting wider. Science is already offering solutions that are ready to go, but without the necessary resources, these successful trials run the risk of forever remaining just isolated experiments. At the same time, there is another equally urgent task. The surviving patches of primary forest need to be protected right now. No amount of genetically selected seedlings will ever be able to replicate the complex ecosystem that has taken centuries to develop in old-growth forests. An old-growth forest is about much more than just trees reaching a certain age. It contains complex soil structures, fungal networks, and highly specialized species, many of which simply do not survive once their habitat is destroyed and never return during the restoration process. If a patch like this disappears, the loss becomes irreversible on a human timescale. Planting new saplings might bring back the trees, but it cannot quickly recreate the deep connections and processes that have been building up inside the old forest over many generations. It becomes a twofold challenge. You have to protect the surviving forests and restore the lost ones at the same time. Both efforts require funding and compete for one limited budget, so a lack of funds weakens each of them. There is a real price behind the lack of funding, and nature is paying it right now, not somewhere down the line. As long as these programs remain limited, individual species keep dwindling, and some ancient evolutionary lines are steadily creeping toward extinction. The flora of the Gondwana rainforests includes over 200 species of paleoendemics. A large portion of them is already recognized as endangered, and losing them threatens to wipe out unique branches of ancient evolutionary history. Among the Gondwana trees, you can find representatives of all three critical categories on the international threat scale: vulnerable, endangered, and critically endangered. Each of these categories means more than just being rare. It means a real closeness to being lost forever. For these species, extinction carries a special weight. Many of them are the only living representatives of evolutionary lines going back tens of millions of years. When they die out, it is not just populations that perish, but entire branches of life's development on Earth. There is one example that makes this threat especially clear. A plant grows in the Nightcap Range area that is known to exist in just one single location. Its genus includes only one species, and that species itself is classified as endangered. A monotypic genus means that it contains just one single species. There are no closely related species capable of continuing this evolutionary lineage, and there are no other known populations that could keep it alive anywhere else. That is exactly why the extinction of a plant like this means losing much more than just one species. An entire branch of the evolutionary tree dies with it, and no genetic program could ever bring it back, because once it is gone, there will be absolutely no material left to work with. Humanity has already changed the fate of these forests, regardless of whether it was a conscious choice or not. Their size has shrunk, the threats have grown, and the future of these ancient evolutionary lineages now depends entirely on the steps that will be taken over the next few years. Now all that is left is to figure out how to use this power. We have to decide whether to protect the surviving forests, help species adapt to the changing conditions, or limit our involvement, while fully understanding that doing nothing is just as likely to change their fate. And the trees, meanwhile, keep growing. Slowly, just as they always have, unaware of any registries, threat categories, or recovery programs, they reach upward into the exact same humid air that their ancestors breathed. They have no idea which seeds people are trying to save and which lineages they want to keep going. The forest lives by its own ancient laws, while mankind searches for a way to give it back time. time that is running far too short for the forest to adapt on its own. For 50 million years, these ancient lineages got by without anyone helping them. Now, their fate is being decided on small plantations where people sort through seeds, grow seedlings, and try to preserve what nature spent millions of years creating. The ancient lineages that survived the splitting of continents, climate catastrophes, and the extinction of countless species now depend on decisions being made today, quietly, without any loud slogans, on small patches of land.